This is Unit 2, Topic 6, Introduction to the Binomial Distribution. So far in probability, what we found is that we could only calculate a probability if we were looking at all or nothing. So the probability that all of something happened or the probability that nothing of that event happened. With the complement, we were able to find just a few other probabilities, but in general, this isn't typical of the way that we would find probabilities. We would normally want to find some sort of situation that we can mold our scenario to. The one that we are going to be looking at in this topic is the binomial distribution. There are 4 requirements that must be met in order for a scenario to meet the binomial distribution. One way that you can think about these 4 requirements is with the acronym BINS, B-I-N-S. So the first requirement is that there must be exactly 2 outcomes. And when you think of binomial, bi is the prefix meaning 2. So exactly 2 outcomes means that there should be 2 outcomes. So B for binary. So the 2 outcomes are typically referred to as a success and a failure. But it's not a literal success and a literal failure. For example, a success could be the probability that that somebody comes down with the flu, given they were exposed to it. So in that situation, a success could be that the person came down with the flu. Definitely not a literal success, but it's more of what we are focusing on in the example. So second is independence. So the trials must be independent, and this includes independence by the 5% guideline. So what trials being independent means is that the results from one trial do not affect the results from the next or other trials. So we'll look at a few of these specifically. Because of the 5% guideline, which is kind of invisible but is important, we don't really have a failure in independence too often. There must be a fixed number of trials. So that's n is what we refer to as our sample size or our number of trials. So this is n for number of trials. And then lastly, the probability of success must be the same for each trial. So these two, the independence and the success remaining the same, go hand in hand every time. So the acronym BINS, binary, 2 outcomes, independence, fixed number of trials, and the success must remain the same. So that's how I'm going to kind of go through it with our examples for this section using the acronym BINS. One thing that is really important, especially as we go forward and we're using different technology, software, and statistical tables, is notation. We've talked a lot about notation before. We are going to get just a few more in this section, but they continue to be used throughout the rest of the course, so definitely worth memorizing at this point. So the first one is N, which is the number of trials or sample size. So this one we've seen a little bit, but not formally. X or K is the desired number of successes in N trials. I've used both X and K, and depending on if you Google it, you will see either one. I like to make a point to mention that it could be either one just because they are both very common. P refers to the probability of success. Q is the probability of failure. And P and Q are always going to be complements because there's only 2 outcomes. So we're going to be applying a lot of those probability rules as we go forward. So since they're complements, their probabilities summed together is equal to 1. Or a lot of times you're given the probability of success and you need to find the probability of failure. So I always go back to the 30% chance of rain, 70% chance of not rain, and I always kind of use that in my examples as I think about the complements. So we will be finding the mean and standard deviation of a binomial distribution scenario, but it's not in the typical way. We don't have a big list of raw data. Instead, what we know is how many trials we have, how many successes we're looking for, and our probability of success. So once we find that we do have a scenario that meets the binomial distribution, the mean is going to be mu because that's for that population, that entire event, every way that that can occur, is n times p. We will look at this in the next section. And when we actually use this, we'll see that it does kind of make sense. So this does what you think it would. The standard deviation is the population standard deviation, and that's going to be the square root of n times p times q. And again, we're not going to actually get a chance to do these until next section, but it's worth mentioning now because it's kind of, everything we need to know about the binomial distribution in this part 1, and then we do a lot more practicing in part 2. So there's a number of ways that you can calculate the binomial probabilities. As always, there is a way to do this by hand. We're not going to do one by hand, not even for fun, which is what I joke usually when we do one by hand before we get to the calculator. I kind of say it's our initiation. In this case, we're just going to go with our calculator or our software output. So I will give you the formula for it. It is something that we could do by hand, but it's also kind of long, so there's a lot of chances to make mistakes when there's more calculations like that. So we'll talk about that in the next slide. You can use statistical tables, which we will be using. You will get an example of this, and you will use it for your exam. And then using technology such as a calculator or software. So calculating binomial probabilities by hand, again, is something that we absolutely could do. But the only new thing here is this exclamation point notation. We're not going to go through that, but we could. It's pretty straightforward. So this is something that we could do. This ends up being a fraction times something raised to a power times something raised to a power. And honestly, this is something that we could have done in our probability section, but it would take us probably 3 or 4 more days to get to it, and it's not something that's important to know how to do by hand. It's more important to understand what the binomial distribution is, when it applies, and how we find those probabilities. So if you wanted to do a few by hand for fun, you definitely could. You'll have to Google what a factorial symbol is or send me an email, but if you wanted to, you could. One way we will actually be calculating these probabilities is using statistical tables. A lot of people will say, oh, people don't use statistical tables very much anymore, but they're definitely still used. I don't know if they are used commonly, but they're really, I don't know, I think they're still used. I probably wouldn't use them myself because I always have access to a computer, but we're going to be using them because, first of all, they're really, really convenient. So we've talked about convenience before, and this is one of those cases where having something in front of you without having to do a lot of calculations on a computer is possibly handy. There's a serious limitation, but we'll get there. So this is an example of a little excerpt from a statistical table. When you get the statistical tables, which I will show you where they are right now, they're located in 2 places in Moodle. So the first is it will be under, which it will not be grayed out for you, but under the week 6 or topic 6 material in week 5. So here they are right now. The rest of the stuff isn't up there yet. And they're also in the folder in the main heading section, statistical tables and reference tables. There will eventually be more stuff here, but for now they're just statistical tables. So if you want to get a copy of those, everything that you need for the exam will be given to you. So you do not need to bring them to the test, but they're definitely something that I would get used to using since they will be on the exam, even if you've decided you want to use data for the most part. So this is a little snippet of that table. It's actually the first few rows and columns. So to use the statistical tables, you need 3 things. You need to know how many trials you have, how many successes you are looking to get, and the probability of success. The cell where your rows and columns meet is the probability for that scenario. So for example, we're going to do this one backwards. The image to the right has a cell that is shaded in green. So this is our probability that it is our answer. So this is the probability of getting 1 success out of 3 trials where the probability of success is 0.15 or 15%. So normally we will not be going backwards, but it will help eventually when you go forward. You're just kind of lining up where all of your 3 values meet. So we'll practice a bunch of these coming up. So next is finding binomial probabilities in Stata. For now, I'm just going to kind of do a brief overview of this, but in the next section, there's going to be lots and lots of practice problems, and I'm going to do at least half of them in Stata. So for this section, I am going to do just a few of them in Stata to kind of introduce, but there are two options. Sometimes having options is good, sometimes having options is bad. But in this case, I'm going to give you both, and it's going to be completely up to you as to whether you want to just choose one and go for it, or whether, one is more convenient for you in some cases and one is more convenient for you in the other. Then you can go back and forth. That is completely up to you. So the first option is using the drop-down menus. The advantage of the drop-down menu is you just put numbers in boxes and tell Stata to just go for it. The disadvantage to this is that the output that you get is going to be pretty long, and sometimes you might have to run the calculator a few times. So this isn't worst case scenario. There's going to be lots of times where you're going to have to run a test or something more than once, but it depends on your personal preference. The second option is typing in a command. Typing in a command is really similar to actual programming, and there's two commands that we're going to be using. They work the same every time, but the downfall is that they're really picky. It's case sensitive, but for the most part, you can copy and paste things that you've done in the past that work and just change your nx and your nk and p values. The advantage is you can always get the answer in one step, although sometimes you might choose to make more than one. So honestly, I prefer option 2 because to me it seems more straightforward, but that may not necessarily be the case for everybody. So again, you only need to learn one of the options. You don't need to know both. If having two options to you is very intimidating, I would just pick the one that looks the best and start there. Maybe eventually you want to add on the second method after you get a little bit more comfortable with the first one, but it is completely up to you. So here are some instructions as to how to do this in Stata. I'm going to demonstrate this, but I'm not going to review it on this slide since I will be demonstrating it later. And so then this is for option 2. We do have a new letter here. I'm just going to emphasize that before I change the slide. This new letter is not really going to add much different at all. I actually only use a different letter to distinguish between these two. So let's actually do some practice here. Determine if the following meet the conditions for the binomial distribution. If it does, explain how all 4 conditions are met. If it does not, explain which condition it violates. So it doesn't matter if it violates more than one. Once it violates one of them, it's game over. So once you find a violation, you state what it is and then you keep moving. So in the United States, about 40% of the people have brown eyes. 10 people are randomly selected, and whether or not a person has brown eyes is recorded. So I'm going to again use that BINS acronym. So the B in the BINS stands for binary, and that is 2 outcomes, which we do have in this case, because we're looking at whether the person has brown eyes or does not have brown eyes. The I in BINS is for independence. Since we're randomly selecting, we're not going to have one person affect the other. So if I randomly select one person in the United States and say, hey, what color are your eyes? Or I look at them. And then I randomly select somebody else. The second person has no effect on the first person at all, and vice versa. So we do have independence here. When we have an example where independence fails, that's where this idea will come full circle. So next, there is a fixed number of 10 trials. So that's just because it says they're selecting 10 people. And then lastly, the probability of success is 40% each time. Now, this is 40% each time because of the 5% guideline. So if we took one person and whether or not they were eligible to be selected again, there's so many people in the United States that it's not going to matter what happens with the first person, whether we select them or put them back, because there's so many. It's just going to not affect the rest of the population. So this does represent the binomial distribution because all of the requirements are met. So next, 20 current Casper College students are randomly selected and ages of the student is recorded. So first problem here that we have is the only one that we're going to mention. I don't think we actually have any other problems. Well, I guess probability of success would be a problem. But in this case, we're going to fail the B. There's more than 2 outcomes because we're recording the ages. It's not like you're only eligible to come to Casper College if you're 18 or 45 or 19 or 28. You can come to Casper College no matter how old you are. So there's definitely more than 2 outcomes here. So once we found a requirement that fails, that's all we need to say about it. A 6-sided die is rolled until 7 5s have been rolled. So we keep rolling until we get 7 5s that we've gotten as a result. Well, one of the problems that we're going to have here is that it doesn't specify how many times we can roll. And we can, roll it 7 times and get 5s every time. We can roll it in theory 1,000,000 times and not get 5 7s or 7 5s. So there's not a fixed number of trials here. It's, just roll until you get that criteria. All right, and then lastly, 45% of the population has type O blood. 15 families are selected and the blood type of each member in the 15 families is recorded. There's actually going to be a few failures here, but the main one is the independence failure. You're going to have a failure of independence because if you're selecting a family, if one person is a certain blood type or the blood type that somebody is, the more likely that the other member in their family is to be that blood type. So this refers back to that example we looked at in the probability with how blood type is very dependent on race. This is also going to be a failure of the number of trials because it doesn't say, 15 families of size 3 are selected, or 15 families are selected and 3 of the members are polled. So that would also be a failure of the sample size, the N requirement as well. So calculate the probabilities using the binomial tables. I'm also going to use Stata just to do an introduction in this section. The next section doesn't have much new material at all, but it is going to be, pretty heavy duty in terms of practice. So I'm definitely going to introduce Stata in this section to get it kind of familiar first. So this is the same thing from example 1. Determine the probability that 6 people have brown eyes, and the scenario previously was 6 out of 10 people that we're selecting, and the probability of a person having brown eyes is 40%. Well, first let's follow the directions and use the statistical tables. So I actually kind of moved up one of these rows here because I think 10 falls in about the middle of the page. So let me just demonstrate how that happens. So these are what the statistical tables look like. So we have 10 trials that we're going to be looking at. So 10 people selected. So I'm going to first find the page that has 10 successes. 10 trials. So this row here, I kind of cut and paste and moved up to the top so that I could clearly see the bolded numbers along the top row. So I'm looking for 10 trials and I want 6 successes. So I'm going to look at the 10-6 row. And as I scoot over, I end up getting 0.111. And the reason I stop here is because this is the row that has 0.4 or 40% for our probability of success. So out of 10 people, the probability that 6 of them have brown eyes that are randomly selected is 11.1% or 0.111. So a note here, this was highlighted in the other slide just to emphasize what's going on in the tables. Anytime it says less than 0.001, this is actually a 0 plus. So you don't put 0.001 in your calculator, you would just put 0 in there because it's not saying that it is 0.001, it's saying that it's some number that is smaller than it. So it's rounded down to 0 basically is what this is saying, but it doesn't want to apply that it's 0. It just wants to say that it's really small. Explain how the given problem meets the requirements for the binomial distribution. So this was according to the paper Debt Literacy, Financial Expenses, and Over-Indebtedness from the Social Science Research Network. 35% of credit card users pay their bill in full each month. 5 credit card users are randomly selected. So we're interested in seeing if we, did an examination of 5 people, what kind of results would we expect here? So going to our acronym BINS, there's 2 outcomes. They either pay their bill in full or they do not. If they're randomly selected, one person paying their bill in full doesn't select another. However, again, if we selected a family, they're probably going to have similar characteristics when it comes to usage of credit cards, so that probably would fail independence. There's a fixed number of 5 trials because we are selecting 5 credit card users. And then the probability of success, which is paying their card in full, is 35% each time. So this meets the requirements for the binomial distribution because it has all 4 of those elements. So find the probability that exactly 3 of the 5 have paid their credit card in full. So this is again going to be using the statistical tables to begin. So the probability that 3 out of 5 have selected, randomly selected, will pay is 0.181. So again, I'm going to demonstrate this here. So I want to go to 5 for our number of trials. So there's 6 rows that have a 5 for number of trials because you can have 0 successes all the way up to 5 successes. We are specifically interested in having 3 successes. So I'm going to highlight the 5-3 row, and then I'm going to go to where this row meets the column with 35%. So we end up right here of 0.181. So 35% meets 5-3, that's 0.181. So the last question says, create a probability distribution for this scenario. So this scenario is 5 credit card users are being selected. A probability distribution has every single option that you can get. So I actually didn't fill this in because I wanted us to make this together. So we have 2 columns here. We have X and the probability that X happens. So I'm going to center all this just out of, visual appeal here. So our options are 0 people can pay their credit card bill. 1 person can. 2 can pay their bill in full. 3, 4, or 5. So these are all of our possible outcomes for this scenario. Now we need to find individually the probability that none of those people pay off their bill in full. 1, 2, 3, 4, or 5. So I would probably use the table. Eventually we're going to go back and use Stata for this example. And so we're interested in just the numbers. Oops, there we go. Just those numbers that are in the 0.35 column. So the probability that out of 5, 0 people pay is 0.116. Out of 5, the probability that 1 person pays their card in full is 0.312. So I'm just going down this column over here. So this would be the probability distribution for this scenario. I just needed to go one more, but the highlighting isn't column-based, it's row-based. So the only other thing that I would do to this to make this complete is I would state what my X stands for. So I would say X is the number of people that pay their credit card in full. So that's the only thing that I would do to this in order to make this complete. But this is a probability distribution because it describes all of the outcomes that we can have. So 0 people could pay their card in full, 1, 2, 3, 4, or 5 could pay their card in full. So I'm going to go back to this question right here and perform this calculation using Stata. So with Stata open, I cleared this is why it's so blank. The way that you get to the binomial calculator, and this is actually running a statistical test, but we're just going to kind of extract the probabilities out of it. So you go to Statistics, Exact Statistics, and then we want to select the Binomial Probability Test Calculator. This has a box pop up. So we have a total number of 5 trials. We're interested in getting 3 successes, and our probability of success is 0.35. So this is good because it just tells you verbally what it is expecting to go in these boxes. It's, you can use these clickers if you want. Now you have to check the box under Advanced. So depending on your settings, it might default to this and it might not. So it should be 53.35, and under Advanced, you should have this box checked. Now you can either hit Submit or OK. If you hit Submit, this box stays open, which I think is an advantage because it makes it so that you can recalculate. So I'm actually going to try this and get it wrong. Let's say I had switched my numbers, which will happen a lot. It's going to get mad because it says the number of successes invalid. Now, if you think about why that would be the case, you're saying that you have 3 trials and you want to get 5 successes. So this is basically telling you that it's impossible, which it is. So let's now look at this using option 2, which is typing in the command menu. So anytime you want Stata to tell you something, you're going to type in the word display first. And the command is binomial p to find the probability of an individual success. So the order of these is important. It's going to have the number of trials first, separated by a comma, the number of successes that you're interested in, and then the probability of a success. So you have a few options here with errors you can get and what it is okay with. So let's say you had a typo. Let's say you accidentally left out the second I in binomial. It gets mad and says, hey, I don't know this function. So I would actually read these errors that comes out here because it'll give you a good idea of what's going on here. So another thing is, let's see, what else can we do here? You can shorten display to DI. So that's just, I don't know, for efficiency. I'm not as much of a fan of the way that looks, but it is efficient. Now, one thing that you probably will do is forget to type in display. If that happens, it says command binomial p is unrecognized. So if it gets you this error, you're just going to have to remember that you have to type in display. So display every time you type in the command window if you want it to tell you something. If you wanted to actually do something like it we did when we did the mean and standard deviation of a frequency distribution, then it doesn't need to tell you anything, it's just going to do it. But you want it to say, hey, tell me these probabilities, so you have to type in display first. So now let's complete the last example using both the drop-down menus and the command box. So I have a bunch of stuff here, let me clear this out. So again, we are going to go to exact statistics and the binomial calculator. So this is going to be a little weird. In order to get the extremes, you have to type in the highest number of successes possible, and then it will give you both of them. So this is one of the things where the drop down isn't always the best way. So I'm going to show you an example of both of those. I'm going to also try to remember to not hit submit or hit OK. So if you type in 0 here, the probability of 0 doesn't appear. And so this is because this isn't actually a calculation that we're having it do. We're just sort of getting what we need out of some statistical test. So if you want to get the least number of successes, which will always be 0, then you need to actually do the maximum, and you'll get both of them. So 0 and 5, you'll get those together. 1 gave us 1, 2, and 3. And so then the only one that we're missing is 4. So people do usually prefer the drop-down menu, but there is definitely, I don't know, I say a disclaimer along with it. What I would do is I would copy and paste my heart away. So I would type in the first command to get the probability of 0 successes. And then I would move this on up by copying and pasting. And so then there are my 6 probabilities. If your probability wasn't a multiple of 5, you would not be able to use the statistical tables. So you do need to be able to use Stata somehow for this, but it will not be on the exam. So that's one of the good things. So I would just match up my probabilities. So 0.116, 0.312, 0.336, 0.181, 0.049, and 0.005. So this is the end of this topic. In the next topic, we are not going to learn any new concepts, but we are going to just practice some more heavy-duty calculations. As always, if you have any questions, please feel free to email me.